G'day everyone. In this chemistry help video, we'll be looking at some of the common traps students fall into when examining changes to equilibrium systems. Blindly using Le Chatelier's principle to make predictions, or using collision theory to give explanations, can lead you into problems if you fail to understand the underlying reasons for the shifts in equilibrium position, which are always rate related. Remember, a change to the frequency of collisions or collision energy are the only two things that can change the position of equilibrium. Only factors that affect the collisions of the species in an equilibrium expression can affect the concentrations of those species. The following example shows our first common trap. What would be the effect of adding more solid sulfur to this system? If we blindly use Le Chatelier's principle, we may view the imposed change to simply be added sulfur and conclude that the reaction would shift to the left in an attempt to minimise the effect of the imposed change. This should use up some of the extra sulfur while reducing the sulfurous acid and raising the S2032- ions and the hydronium ions. In fact, this is actually quite wrong. The addition of extra sulfur has no impact on the collision frequency, as it simply sits on the bottom of the reaction vessel, which already has unreactive sulfur there. As there's no impact on the rates of either the forward or reverse reaction, there'll be no shift in the equilibrium position. This is very much like the real life situation where you have a cup of tea or coffee and you add some sugar. If you add spoon after spoon after spoon of sugar, eventually you reach a point where no more sugar will dissolve. If you put more sugar into this system, it simply falls to the bottom. It doesn't taste any sweeter. There's no change to the equilibrium position simply by adding more solid to a solid system that is already saturated. What happens when we add additional water? Students will often look at this situation and say that as water is not in the equilibrium expression, adding more will make no difference, just like the solid example we went through. However, when extra water is added, we are actually diluting the system. We increase the space in which the species exist, and in doing so decrease their concentration. It may be likened to a gas system, where there are more gas particles on one side of the equilibrium equation than the other. If we add water, which is basically increasing the volume in which the ions move, this will impact on their collision frequency, as the concentration of all ions is effectively lowered by this change. The rates of the forward and reverse reaction are both lowered, but not proportionally. The forward will be lowered more as it has more particles. This will create the classic overtaking scenario where the rate of the reverse reaction is, for a time, higher and shifts the concentration towards the left. Here's another example from an exam. We have a situation where hydrogen sulfate ions are reacting with water to form sulfate ions and hydronium. What is the effect on the forward reaction rate when distilled water is added? The concentration of all species goes down, and the rate of the forward and reverse reactions decrease. However, the reverse reaction, which has more particles, decreases more. The forward reaction overtakes the reverse until equilibrium is re-established. The result is that there are less particles, a lower concentration, therefore a lower collision rate. The second part of this question is really tricky. What happens to the resulting pH? Adding water caused the previously mentioned changes. The equilibrium favoured the right, producing hydronium. So some students answered and said there was to be a decrease in pH. But this is really wrong. Remember, first the solution was diluted, lowering the hydronium ion concentration. Then it shifted right to partially replace the hydronium. The net result is a decrease in hydronium ion concentration, and therefore the pH goes up. You could never make enough hydronium ions to restore the pH to its original level once you've diluted the solution. Here's trap number 3. For this one, we can use the exam question we used previously. If we add lead nitrate solution, what happens? Well, blindly looking at this, we could say that the lead ions and nitrate ions are not in the system, so no effect, right? Well, no. The lead ions can actually form a precipitate with the sulfate ions, lead sulfate. That lowers the sulfate ions concentration. The forward reaction, which is unaffected by any changes to its concentration, overtakes the reverse and the equilibrium shifts to the right. This leads to a consumption of hydrogen sulfate and an eventual decrease in its concentration. So to answer the question, what is the effect on the forward reaction rate once equilibrium re-established? Well, it's been decreased. Here's trap number 4. We can get so used to looking at rate and concentration graphs that when we're asked for a pressure versus time graph, we can get thrown. If we have the Haber process, as we've seen before, and the temperature is increased, we know that the endothermic reaction will be favoured, and the reactant will shift to the left. The graph will look like this for the concentration versus time graph. What we need to remember is for systems that consist of only gases, we can substitute pressure for concentration. When we increase the temperature, we increase the kinetic energy of the particles. Where the particles move faster, they hit the walls of the container with greater force, and the pressure increases. So when we graph it, we need to show how that temperature increases the pressure initially. Then we can graph as usual. So they were the common traps that you might come across. I hope that's helped you, and we'll see you next time.